Hi, y'all. I'm going to quickly go over some of the products and the mechanisms of the following reaction. Also, I realized for my fall 2024 class, this is when I'm doing this, there were some on here that actually, like the decarboxylation that's not one that I covered yet on this chapter. It's in the next chapter, actually. So I just wanted to point that out. I think the rest of these, though, were accurate. Yeah. Okay. No, not the haloform either. Okay. All right. So the first one, this is a Wittig reaction, and I know that because this PPH3 is like quintessential Wittig, and it does form a yelid where the negative and the positive sort of go across from one, or like separates out, where you have the negative and positive instead of it being a double bond, like as a resonance structure. But I typically find it easier to draw like this. And what I do is I usually line up the heteroatoms. Let's see, we have 1, 2, 3 carbons, 1, 2, 3 carbons. And then the chain here with the phosphorus and the 3 phenols, or sometimes they actually have them drawn out. And then I line that up next to this one. And this forms sort of like a box mechanism where this attacks here and this attacks here. And so you get this box with the phenol and the oxygen, these 2 carbons. And then over here you get this structure like that. And then the reaction will happen again, where we have this bond right here break and this bond go here. And so then you end up with a double bond right here between these 2 carbons. And then I forgot to draw the 3 phenols here. And then you have a carbon-oxygen double bond. You have a phosphorus-oxygen double bond and then a carbon-carbon double bond. And it keeps the same R groups that it had to start with. So this one's a pretty easy one to notice because this is this is like a very weird color that we have going on here. I just noticed that. Maybe I can do this. Might be a little bit better. So right here, this is like an easy one to notice because you have that phosphorus. Like this is always an indication that whatever this is double bonded to and whatever this is bonded to, they're going to make a double bond to each other. So it's kind of the easy one to notice. Okay, the next one is if an equal amount of compound 1 and compound 2 are mixed with excess NH3, which would react more quickly and easily, and why? So when I'm looking at this question, which one of these would react more quickly and easily, I'm looking primarily here at the carbonyl carbon. We had a really similar question to this in PLTL this week. But what always happens in nucleophilic or base catalyzed reactions is the nucleophile will be attracted and drawn towards the positive here. So your negative thing or your thing with excess electrons will be drawn towards the positive here that you get when you get your O minus, something like this. And then this is positively charged here. And so the stronger that positive charge, the better. So let's see. Oh, I drew this one wrong. The stronger that positive charge, the more reactive it will be. And so between these two, we have a stronger partial positive on this chlorine than on this ester. And the reason for that is there is a relatively stable resonance structure where this will donate electrons in here to fill in the positive charge on the carbon. So that positive charge is more distributed. So that's one reason we have this resonance structure. Technically, I guess chlorine could do a similar one, but I think having a positive chlorine like this is more rare. So that's part of it, is the resonance, the donation of electrons with the resonance structure. I think you're more likely to get this structure than this one. Then the other thing is the leaving group, is that chlorine is better and happier as a Cl minus. It's a weaker base, which means it's a more stable leaving group than the CH3O minus. And the way you can know that is you can look at the pK of their conjugate acids. So the pK of this is 16 to 18, while the pK of this is like, I think, negative something. So it's like much more acidic, which means this is a much weaker base, a stronger acid, weaker base. So this is a stronger acid. This is a weaker base. And so that means it's less reactive after it's left. So you want to consider both how stable is the leaving group after it leaves and how electrophilic is, like how much of the electron density, the absence of electron density here is attractive to the what was I going to say? To the nucleophile. So that's what I think about. Okay, so the next one, draw the reaction mechanism and the major product of the reaction above. So we know acid chlorides are the more reactive. So we're going to have the acid chloride react with the amine. And it's excess amine. So that basically is like saying it's base catalyzed. So this is going to attack. And we'll get O minus NH3 Cl. Anytime you have any kind of base or nucleophile with your carbonyl carbon, it'll be attracted to that same place right there. And then because chlorine's a good leaving group, like we just talked about, it'll be pretty happy to leave. So we'll have NH3 double bonded here. And then you get this. So plus Cl minus is present as well. And the excess NH3 is to basically, you could get a transfer of protons here that would make this be NH2 minus and HCl. But if you have excess amine, it'll cancel that out. So that's the major product over there. Okay, the next one is propose a Grignard reagent that could be used to accomplish the following, then draw the reaction mechanism of the reaction. Okay, so when I think of Grignard reagents with ending up in alcohols, I know that, and seeing this right here, I know that a lot of times Grignards will attack right here and give you the O minus with the chlorine and the R, and then they'll restore and kick out your leaving group. And a lot of times, because this is so nucleophilic, it'll actually attack again, and you will get O minus and 2 of your R groups. And so when I look at this transformation, and I know it's supposed to be a Grignard, and I know this is kind of the main idea, I'm looking at these 2 R groups that are the same. And these 2 R groups both are, it looks like the bond forms from 1 carbon. It looks like this to me, where we have 1 carbon here and then this, so a phenyl. And so if we had and the bond forms from this carbon to the carbonyl right here. So if we had something that looked like this, that would be able to attack and kick up. And you'd get O minus and then Cl and then this structure bonded on. And then it would restore and kick that out, and you would get this. And then this thing could attack again. Oh, wait, it's 1 more carbon right there is where the lone pair goes from. And it looks like O minus. Here we go. And then another one of these down here. And then we'd have to add acid to get this to be an alcohol. So that's the thing I'm looking at, is this R group right here is like whatever has been added on twice. So that would be the thing that does it. And I always work out the reaction just to make sure it works like I thought it would. But it didn't ask it asks specifically for the Grignard reagent, so I want to draw this in the Grignard form, which is this plus MgBr. It just is roughly equivalent to this carbon ion, so technically this would be the answer that you're looking for. Okay, so this next one, draw the reaction mechanism and product of the following reaction. So again, whenever we have an alcohol present, it's going to attack the nucleophilic carbon. Normally, this is in the presence of acid. I should have written that acid would be present. So the first step would probably be the ketonium formation. And that looks like this, where we have the ketone that's protonated. And then this would be nucleophilic attack, or this is electrophilic. I'd have to draw this weak nucleophile, a relatively weak nucleophile. And we'd get OH here, and then a new bond to our OH CH3, and that'd be positively charged. And then the next step would be the same thing that we've seen a lot before, when you have your good leaving group and a nucleophile attacks it, this kicks up and you get O minus with your leaving group and your nucleophile, and this comes down and restores. So that would look like this. Well, in this case, our leaving group would be this oxygen right here. It's not the best leaving group, but if you get a proton transfer, OH and OCH3, and this becomes OH plus, then you can get your ketone to restore and this to leave. And so I actually leave this in the ring at first. If this bond breaks, I leave it in the ring shape because I think that's easier to see. And then I go up and over and OCH3 and O here, it would still be protonated, H plus. That looks kind of weird, but I think drawing it like this initially helps. And then I usually will try to redraw it in a way that makes more sense. So I do like OCH3, O, and then I go around the ring here and say OH. And then this is still protonated, so we need a deprotonation step. And we often will see this drawn out. So I'm going to number my carbons, 1, 2, 3, 4. Carbon 1 has this oxygen here, and this oxygen with the CH3 off of it there. So 1, 2, 3, and then 4 has this OH. And we also can assume that we lost a proton. You don't have to draw the mechanism, but just know that you lost the proton here, and you'll end up with this final product. So you basically just swapped one ester out for another here. Okay, the next question, for the following product, or predict the product for the following series of reactions. You'll need to be able to draw the mechanism for step 4. So that's going to be very similar to what we just did, but base catalyzed instead of acid catalyzed. The first part is remembering that toluene looks like this, and orthometapara means that the chloro is exactly opposite it. And then if you react that with the reagents listed in I, this basically will take any R group that's not tertiary. So any R group here at all that's primary or secondary will be converted to a carboxylic acid as long as it's off of a aromatic ring. And the first step is actually O minus, and then adding the acid makes it to the OH. So that's 1 and followed by 2 gets us here. Then SOCl2, you don't need to know the reaction mechanism for this, but will convert your carboxylic acid to a chlorine. And then if we have that in basic conditions, then we can assume that we have CH3O minus, and that will be a good nucleophile, and it will attack. And you will get, you still have a chlorine here, O minus, Cl, and OCH3. This will restore and this will leave. And you end up with Cl, O, O. So we basically converted our chlorine acid chloride into an ester. You would also get plus Cl minus, so you'd need to add some kind of acid to get that back to neutral ultimately, but that would be your final product. Okay, the next one, this first part is a reaction you've done in organic chemistry lab. So the first part is making a Grignard reagent, so we just make this MgBr, basically just inserts in. You don't need to know the reaction for that part. And that is roughly equivalent to this carbanion with CO2. And that would attack and go out like that. So we would get this part is unaffected. There's one part carbon double bond to an oxygen here, and then an O minus. No good leaving group to kick out or anything, so it stays like that. So we add acid, and we get our carboxylic acid. So that's step 2 was with the CO2, and 3 was with the acid. And then again, SOCl2 does something very similar to what we saw up above here. It's actually the same, just minus the chlorine, where we get a chlorine. And then with our chlorine with an amine, the overall reaction is, I didn't draw the mechanism for H+, but that's basically the mechanism for question 3. The overall reaction when we have any, less reactive carboxylic acid derivative with a more reactive carboxylic acid derivative is to have this attack and basically just trade places. So we get our O minus, Cl, and NH3, and then this comes back down and kicks it out. So you get an amide. And if you're not sure why, I did a whole video going over carboxylic acid derivatives and why the reactions happen the way they do, which might be a good little video to watch before if you're unsure about this one. Okay, and we're going to see the same mechanism again, where LaH is this lithium aluminum hydride. So there's 4 H's, and they're all, this is negatively charged, and then we have a lithium that's positively charged. So this H will act as H minus basically and attack here. So again, we're just getting that same mechanism where we get the nucleophile add, you get an H here and a chlorine, then this restores, this kicks out, and you get an aldehyde, but this aldehyde is going to be even more reactive, so you're going to get, it's even more nucleophilic than, is it more nucleophilic than the acid chloride? Now I can't think off the top of my head. But you'll get another acid, or another H minus attack. So that's step 1. No leaving group can leave, so we're stuck here. So now we'd add in our water. This would take a hydrogen from the water, and you'd end up with OH. And I'd actually probably, with these 2 hydrogens here, and you don't necessarily have to draw them in. It would look correct this way too, they're implied. I actually would probably do H2O and a little bit of H plus to counteract any base then this would make OH minus, but just some source of protons will get you that alcohol. Okay, so propose the reagents needed for the following transformation. So we had talked about how acid chlorides are the most reactive, and then acid anhydrides. We haven't done a ton of reactions with those. And then esters. And then amides. And if you're trying to convert this way, so this is more reactive, and this is less reactive. So you have a good leaving group that will leave here, and it's going to be stable, and it's not likely to attack again. And these are, so therefore these are more electrophilic here as well. So this is more reactive, this is less reactive. And you can easily just convert from here to here by adding, basically either in acid or basic conditions for a lot of these, just whatever thing you want to replace it with, an acid or base, NH3 here, any of these things will get you what you want, but you can't go back this way the same way. If I add an O- to the amide, it's not going to go to an ester because O- is less reactive than NH2 minus. So it's not going to go this way. You can only go this way. And again, go back on that video that we talked about. But all of these can be converted back to carboxylic acid. And carboxylic acid can be converted to any of these. So if you're trying to go back this way, a good intermediate is to go from here to carboxylic acid and then carboxylic acid back to that thing. So to get an amine to carboxylic acid, H plus and H2O with heat will do it. You can also do base catalyzed conditions, I think. And then the next step would be SOCl2 to get carboxylic acid to chlorine. And if you're not sure why, again, I think watching that video of all the reactions with carboxylic acids will really be a good first step. Also in your PLTL, I encourage you to make a little review of all the reactions. They'll really make a big difference. Okay, so again, we have alcohol, and pyridine is in basic conditions. So this nucleophile will be attracted here. We will get O minus, chlorine, and then this oxygen. It'll still have its hydrogen and this ring structure. Probably there will be a proton transfer, but where we go from here to here, but it could also get taken from by the pyridine as well. Either one of those, I don't get too fussy about when protons get transferred. So, I'm not too worried about what stage that happens in. This is now neutral. But as long as you know that then this would restore and kick out the good leaving group, you can worry about the proton transfer whenever it makes sense, as long as you know that at some point the proton is going to get transferred and this will become neutral. And I usually do the proton transfer before the leaving group because if this is not positively charged, then it's a bad leaving group and this is a better leaving group. So that's my thinking, but I don't get too fussy as long as you can kind of get the main idea. Okay, so then we have this structure is formed, and the pyridine, if it hasn't already, pyridine is a good base, and so it'll take that proton and leave this here, and we end up with our ester. So that's the final product. Okay, then next, what are the key steps for the mechanism of the nucleophilic addition of aldehydes and ketones under basic conditions? So this is the reaction we've done over and over. If you have an aldehyde or a ketone with a basic condition, then your nucleophile is likely to be strong, and it's going to attack first here, and then this will kick up. So that's under basic conditions. If we're under acidic conditions, so we did these reactions a lot in class, so hopefully this is ringing bells for you. If we're under acidic conditions, the first thing that happens is the ketone will get protonated, and then your nucleophile, even if it's weak, will easily be able to attack once your ketone is protonated to the ketonium, and then do that same reaction over again. So this is the steps in an acidic condition. And then this is the steps in basic conditions. So you should be familiar with that over and over and know that this is called a nucleophilic addition reaction. Okay, question 12. Predict the product of the reaction below. You should be able to draw the mechanism for step 2. Okay, step 1, you may have forgotten already, but this is, when I see PCC, I think of this as an oxidizing agent. And PCC is one that I believe with primary alcohols, it stops at aldehydes. So if that's the case, then it's like relatively weak. So our first step would be to take this to CH2, CH2, OH. That OH, it basically just adds a double bond right there, but only once. And then when I see that with this NHCH3, I am thinking that this is going to make an imine or an enamine. So with primary, it makes imines, primary nitrogens, and with a secondary, it makes an enamine, which means it has a double bond one away. So the first step here is, this looks like this is an acidic condition. So the first step would be the ketonium formation, just like we drew up here, where basically your aldehyde would get protonated from that. And then your amine will attack and kick that up. And you get, let's see, N, two CH3 groups, and this H is positively charged. And then you have your oxygen here that's with a hydrogen. Okay, so it looks like this. This is going to steal this proton. It's not exactly a proton transfer like that. Technically, this gets deprotonated, this gets reprotonated, but this is a lot of times easier for students, so I typically draw it like this. There's a lone pair right there. Oh, I drew that on the wrong position. Let me draw it again down here. Sorry, I know this isn't the clearest. It is late and I am tired, but I told my students I was going to have this done for them, so I really want to. Okay, so after the proton transfer, let's see, it looks like we have this here and here. And then down here, OH, H plus. So then now this becomes a good leaving group, this protonated oxygen. So this, instead of the carbonyl restoring, this amine will restore, and this whole thing will leave, and you get this sort of protonated imine where you have a double bond to this nitrogen, but the nitrogen does still have two CH3 groups on it, so it's positively charged. And we started with an aldehyde, so there's also a hydrogen here. So then the next step typically with this is, because this nitrogen's not happy being positively charged, the water that got kicked off is going to do an elimination reaction of sorts, where it takes this hydrogen, these go here, and this bond breaks. So you end up with your ene, so that's a double bond one away from your nitrogen. Didn't see it, I ran out of space. Ene, your double bond one away from your nitrogen and your nitrogen. So typically when I think of any carbonyl group with a primary nitrogen, I just know that basically this is going to get replaced with the nitrogen. And, oh, that was the secondary that I drew. And it'll lose its two hydrogens. Those will go by, and you get this. If you have any kind of carbonyl, no matter what these R groups are, with a secondary amine, I always will draw first in as if it did that bond like this. But because it has two things with it, it's positively charged. So then we just have to instead make the bond be one away. We take the hydrogen from here, this goes here, and that neutralizes. So that makes an enamine that looks like this. An ene, double bond, and then amine. So that's called an enamine. And this is called an imine. So all that to say, when I see this carbon-nitrogen double bond right here with an R group, I'm guessing the two reagents that were reacted were this, and probably some acid to catalyze it, maybe base. So this is what I would expect would react to make this. And I'll just pretend that it's base catalyzed. This is gonna, oh wait. If you're not sure, you can always draw the reaction happening. And we could go through all the steps where you would see that this oxygen becomes O minus, this N goes here. This is still positively charged. This would take it. You'd get OH and this nitrogen with hydrogen, and then you'd probably get another proton transfer, and then these electrons would go in, and you'd get this leaving group to leave. I did a really bad job of drawing that mechanism out, but I usually do it quick like that just to double check that I'm right. I drew it out more detailed right here, so you can see the mechanism. And then again up here, that's the overall reaction. And technically didn't ask for the mechanism. I just like to do that to check myself. Okay. Next one. So the first step, we make a thiol formation. And let's see, propanal is a propane. Al is an aldehyde. And then propane is 3. So it looks like this. It says you should be able to draw the mechanism. And I have drawn this mechanism already for this class a few times, both in class and on the last recitation review, I think, of the cyclical thiol formation. And my dinner is ready and waiting, and then I'm going to go to bed. So I'm going to skip it this time. Hopefully, you can go back and find the mechanism in those other videos, but it's just exactly the same as if it reacts like this. We did this several times in class, and I've done it on the past recitation videos, but the overall reaction looks like this. We get this thiol forms. And then I've told y'all that if then you react that with Raney nickel, in the presence of acid, this thiol forms. And then if you react that with Raney nickel, the overall product is that you replace those with hydrogens, these sulfur groups with hydrogen. So you just are going to end up with propane. So that's the final product. This mechanism you don't need to know of going from this thioacetal to the with Raney nickel. It's just a way to reduce the carbonyl. This first part you should, in theory, know, but I've done that several times, so I'm not going to redraw it now because it's a little bit tedious. Okay, the next one, ozone with DMS cleaves, and without H2O2 or another source of oxygens, it does not continue to oxidize. So it's just going to give us an aldehyde here. And hang on, I always have to count 1, 2, 3, 4, 5, 4, 5. An aldehyde here and a ketone here. And then this is an oxidizing agent. So this is already, ketones are, well, I guess I'll go back over and say if you have an alcohol and you oxidize it once, it becomes, you can trade out one of those beta hydrogens for an aldehyde. And then if you oxidize that, it becomes a carboxylic acid. That's for primary alcohols. If you have a secondary alcohol and you oxidize it, it becomes a ketone. So, and then you can't oxidize it anymore because you don't have any more beta hydrogens like right here that you can trade out wherever that oxygen is bonded to the carbon. So that's it. So the ketone over here, that's it. That ketone is done. It can't be oxidized anymore. But if we add another oxidizing agent to it, let me count 1, 2, 3, 4, 5, 6. Then this aldehyde will become a carboxylic acid. So that should be the final product. Did I add any carbons? I don't think so, because on 5 right here it has that. Okay. So that would be your final product, a carboxylic acid. The next question is, how can you change the reaction above to be able to accomplish the same with just 2 reagents? And I mean like in one step. So if you had KMNO4 and some source of heat, it will cleave as well. And like hydrogen, acid, H2O, water, something like that, H3O plus, that will work in just one step. So that's what I was looking for. Okay, what is the mechanism of the following product? So I talked to y'all about how cyano groups could be converted with SOCl2. Wait, I just realized that I think this question is wrong. So this should have been reacting an amide with SOCl2. results in making a nitrile. You basically lose the H, two H's and an O, you lose this water, and it becomes this carbon nitrogen double bond right here. So, and you don't need to know the mechanism for it, just that basically you lose the two H's, you lose the oxygen, and then these three bonds just go between the carbon right here and the nitrogen right here. So I think I just was probably tired when I made this, and this question should have been an amide with SOCl2 makes this nitrile. And then the next question, draw the mechanism and product of the reaction if the nitrile above was reacted with LAH. I don't know if it means this nitrile or the one that's formed. I think that's probably what got me mixed up, is I wanted to do a question with the nitrile, and so I drew it in. But essentially, the H minus will attack the carbon, just like we've seen, and this bond would break to nitrogen. So you'd get your carbon is still have a double bond to nitrogen. We have a hydrogen here. That carbon, or that nitrogen, is then negatively charged because it already had a lone pair that was implied. So then this becomes negative, and it likely will then form a complex with the positive lithium from the lithium aluminum hydride. And so then another H minus will be able to attack, and you get, then you get a fully saturated nitrogen here. It's formed a complex. It might form a full bond. I don't think y'all are going to need to know the mechanism of this for your test, but it does ultimately end up giving you NH2 with this because it attacks here again. I think I wanted you to know the hydride attacks, but this, it's kind of complicated, I guess. But first, it forms a complex with the lithium, and then the lithium aluminum that's left from the aluminum that's left from the lithium aluminum hydride, and you end up getting a fully hydrated amine. So I want you to know that overall reaction, but I'm actually not worried about the mechanism. So I guess I just was not thinking when I included that. Okay, next question. If you hydrolyze is already showing you. If you hydrolyze an amine, nitrile, it gives you an amine. And then if you continue to hydrolyze that, you get a carboxylic acid. So you actually have this exact mechanism in your notes, and this video is already really long, so I'm not going to go over it with you. But if you look in your slides, the very last thing we went over was nitriles reacting with acid to become amides, and then amides reacting with acids to become carboxylic acids, which we've already gone over. And I probably also went over it in the video of the overall review of carboxylic acid. So I'm going to skip drawing the mechanism out for this one and hope you can just review your notes. This one is going to act as an acid anhydride. So this would attack and kick up, just like we've seen over and over. You'll get O minus Cl and then O double bond carbon. This will come back down, kick out, and we've now converted an acid chloride to an acid anhydride. So that's the same mechanism we've seen several times before. 21 is rank the acids shown in decreasing order, strongest to weakest. So when I look at this, first of all, the acidic hydrogen is this one for all of them in a carboxylic acid. And if we were to lose that hydrogen and leave the electrons behind, this would become negative, and we're wondering which one of these, the most willing to give up the proton, is whichever one can deal with that negative left behind the best. One good way is resonance structure. All of these have that. So then the next thing we look at is there an inductive effect, which means is there an extremely electronegative atom that's going to be able to pull the electrons away? And they all have an extremely electronegative atom, and it's right next to the main one. So then we go in order of which one's the most electronegative. So this fluorine is the most electronegative. So I think this one would be the strongest. Then chlorine, then bromine, then iodine. I'm going to write it out like this. This is the number 1 most acidic. This is number 2. This is number 3. This is number 4. And this doesn't have any inductive effect, so this would be number 5. So as we go down the periodic table, these become less electronegative, so that's why. I've seen similar questions where there will be like 2 fluorines right here, or 1 fluorine right here. And so if there's 2 of a strong electronegative, that's going to be more acidic than something like this. And then the further down the line it is, or the less fluorines there are, the less impact it has. Okay. This is a really similar question. It's saying if I have a carboxylic acid and I take away this hydrogen and leave behind the negative, which one can deal with that the best? But it is on a benzene ring, which is a little bit different. But in this case, a thiorbenzene ring, all these have a lot of resonance structures, so they're all going to be really willing to give up that acid. But again, we're asking what can deal with electrons left behind, and electron withdrawing groups, electronegative groups are better at doing that. And so hopefully you remember from our electrophilic aromatic substitution days that nitros are really electron withdrawing. They have a positive charge right there, not NH2s, NO2s. And then chlorine. So this is the most electron withdrawing. This is the next most electron withdrawing. This is electron donating. And then this is even more electron donating. So this would be able to deal with the negative electrons left behind the best, because this nitro is going to be able to pull them away. And so is this chlorine. Whereas this CH3 is actually donating a little bit of electrons, and this OCH3 is donating a lot of electrons. So this would be the worst at dealing with the electrons left behind of this group. Okay, so this next one, what is the rate of migration in a Baeyer-Villiger reaction? So this is an oxidation reaction, and basically what it does is it will just insert an oxygen, and it has a specific order of migration. This is called the order of migratory aptitude, and we went over this in the slides for this Baeyer-Villiger oxidation. It's not intuitive. So the first one is hydrogen's the easiest to move, then tertiary, and then secondary. And secondary I think is tied with phenyl, or it's close, maybe phenyl ever so slightly, then primary, and then methyl. So it's just not what you would think. It's not intuitive at all. But for each of these, you can kind of practice applying that and know, like, okay, so this would make a carboxylic acid if we reacted it with MCPBA. Then the next one we would have, this one is a methyl, and this one is a secondary. So the secondary would go first. So this one you would get this ester form. Between a methyl and a phenyl, the phenyl would go. So you would get... So it's just kind of not intuitive, and it's kind of a weird reaction, but it's also very useful synthetically. So you'll need to know this order of migratory aptitude. The one that would react the first would be the one with the hydrogen, because that's easiest to react. And then after you know that, it's a lot easier to answer these questions. So is that all of them? I think that's all of them. Hopefully that was helpful to you. Sorry this video is so long. But I hope you have a good luck studying, and I'll see you in class tomorrow.